So I'm glad to announce that, or introduce to you Rebecca Fiebrink. Rebecca makes new accessible and creative technologies. As a reader at the Creative Computing Institute at the University of Arts in London, her teaching and research focus largely on how machine learning and artificial intelligence can change human creative practices. Rebecca is the developer of the Wakinator, creative machine learning software, which is used around the world by musicians, artists, and game designers and educators. She's a creator of the world's first online class about machine learning for music and art. Currently, she's working on projects related to creating new accessible technologies with people with disabilities and designing inclusive machine learning curricula and tools. So yeah, I would hand over to you, Rebecca.
All right, thank you. Can you see my screen? Excellent. So thank you
Yes.
so much for having me here today. I'm excited to kick off this workshop. As you just heard, I'm a reader at the Creative Computing Institute at the University of the Arts London, and a lot of my research focuses on understanding how machine learning can be used in creative work. As part of this, I've been building machine learning tools for creative practice and media since about 2008. And I've been teaching machine learning to creative practitioners and other non-STEM students in various capacities since about 2011. So this includes at UAL, previously at Goldsmiths. I have a couple of MOOCs online at Cadenza and FutureLearn, and I frequently teach workshops to professional creators around the world. I'm not an education researcher by training. I'm a computer scientist, but I began to do more formal research on machine learning education a couple of years ago after seeing a real gap in the work in this area. I've recently published a paper about some of my approaches to teaching in ACM transactions on computing education, and a lot of my talk today draws on that work, and I would encourage you to take a look at that paper if you want to know more details. So my students include undergraduate and master's students in creative computing, digital arts, and games, as well as professional artists and creators. Often these students have some competence in programming. Some of them are in fact expert programmers, but many have very little mathematics background. Many have very little background in terms of computing theory or algorithms. So they may be a little bit different from many of the students you are working with. These students have really legitimate interest in using machine learning, but it's not just for pure data analysis, unsurprisingly. They really want to take machine learning techniques and use them to build new things in music, art, design, gaming, and so on. So when I began teaching such people about machine learning in 2011, there was unsurprisingly no machine learning curriculum for such students that I could draw on. I had to figure out from scratch what to teach these students and how to teach them. So today I'm really going to share with you how I went about doing this. Some of the content and activities that I designed might be useful for you to use directly, but even if it's not, because you're working with different students, I hope that sharing the process that I went through and the reasoning that I used in building these courses, and the approach that I took to doing research about my teaching, I hope these might get you thinking about new ways that you could do such things in your own work. So really, this is a talk in which I'll be sharing aspects of my teaching practice and a bit about my research about teaching. I'll start by describing how I established learning objectives for the new courses that I developed. I'll talk about a bit about creating scaffolding tools for experiential learning in these courses. And I'll be describing a couple examples of formative assessments that I've developed and how I've used data from these assessments to learn more myself about what my students are learning from my teaching, about misconceptions and challenges that they might encounter. Again, these are assessments that you might adapt for your own students, but if not, I hope that you might think about how you could similarly use data from your classes to reflect on your own teaching and contribute to research on machine learning teaching. Because, as I'll conclude, there is still really a great need for more research in this area. All right, so let's start with talking about learning objectives. The main type of machine learning I've focused on in the teaching I'm talking about today is supervised learning. If creative students can use classification or regression to build model functions that compute output values from inputs, this opens up a huge space of really useful projects to them. Because machine learning is super helpful in making sense of data from inputs like motion sensors, audio, video, images, data from media and games engines, and many other sources that are relevant to creative practice. And on the other end of the machine learning bit, the classification labels or regression values that might be computed from these inputs can be used to control all sorts of processes of interest to students. These could include sound and music synthesis, procedural animation or design, robots, physical computing systems, game engines, and so on. For instance, here are a few examples of final projects that students in my courses have made. One of my favorites is a spellcasting game. It's sort of a retro feel game, and you move your mouse in certain shapes during the game to cast spells. And for you've got a classifier that classifies which spell you've cast, and that affects your gameplay. Another nice project recently was an automatic voice harmonizer. So you sing into it, it uses a classifier to detect what pitch you're singing, and then based on that, it comes up with harmonies that it plays along with you in real time. There was a really fun sort of whimsical and weird project, which was a digital stress ball. It uses your webcam to track your face and look at how your face is moving, and then uses that information to manipulate this weird 3D object with the intention of getting you to relax somehow. Another cool project was a gesturally controlled 3D graphic generation system, where you use the motions of someone holding an iPhone, both the motion of the phone and their interactions with the interface, to change a procedural 3D graphics system. And you can manipulate this system until you find some sort of configuration of graphics that you like, and you hit a button and it gets sent to a 3D printer to be printed. So these are just a few examples. There's lots of others, and you can find more online quite easily. But the question, of course, is, for me, what do students have to learn in order to competently make projects like these? And how do we teach them? A good starting point for answering questions like this is the concept of constructive alignment, which comes from John Biggs. If you're not familiar with this, the basic idea is that you want all your learning activities and assessments to be aligned to your learning objectives, to the goals for what you want students to be able to do at the end of the course. Now, of course, if we want to do this, we have to know what those learning objectives are, and this merits some serious consideration. As I've mentioned, my overarching goal for my students is to enable them to create new systems using machine learning. If you start to ask what knowledge and skills they need in order to be able to do this, it quickly becomes clear that it's far more than the ability to narrowly create an accurate model from a data set. For them, machine learning is embedded in a design process of building some new thing, and this means that they confront some really thorny questions when working with machine learning. For instance, what can I build with machine learning? What should I build? How do I go about building it? How do I know if it works? How do I change it, especially the machine learning component, if it doesn't work or if I want it to work differently? There's a lot of research about how people navigate such design processes in all sorts of domains. One really useful piece of work that I've used is by Howard, Cully, and DeConnick, who synthesized research from a large number of previous papers, integrating current understandings of engineering design processes and human creative processes. They've identified a set of steps that are common to building nearly any type of new system, whether in creative work or engineering. And these include starting by establishing design requirements, formulating the desired system behavior, synthesis or implementation, really, analysis, or just observing what that implementation does, evaluation, comparing the observed implementation, the observed behavior with the desired behavior, and reformulation. When something doesn't work the way you ultimately want it to, going back and changing the implementation or the formulation of desired behavior or the design requirements themselves until you are ultimately happy with what you've created. And at the end, of course, you probably want to document it before you're completely done. So this became the basis for designing learning objectives for my courses on creative machine learning. I asked myself, what about machine learning do students need to know, and what machine learning skills do they need to have in order to do each of these steps effectively in a new machine learning project? And this resulted in a pretty straightforward enumeration. For instance, thinking about establishing design requirements and formulating the desired system behavior, we have learning objective 1, understand the structure of supervised learning problems and the capability of supervised learning algorithms. And learning objective 2, identify feasible uses of ML in new projects and map a new project idea onto the structure of supervised learning, for instance, inputs, outputs, training data, and model. For analysis and evaluation, we have learning objective 6, choose appropriate methods to evaluate a trained model against design criteria relevant to the project and apply these within the ML tool or library used. Now, many of these fall under what I would say seems obvious to include in any sort of machine learning course, in any sort of standard curriculum, right? Making sensible choices about algorithms, about features, using existing machine learning tools to build models, choosing and applying appropriate evaluation metrics. Others of these learning objectives are not necessarily an explicit part of standard curriculum in machine learning, but they still actually seem relevant to many machine learning applications and perhaps worth making more explicit when we think about what we want our students to learn. This includes identifying feasible uses of ML in new applications, mapping ideas for new ML applications onto the structure of machine learning, reasoning about appropriate mechanisms to improve a machine learning system when it's not working well. And of course, a few of these are also specific to the application domain. For me, for instance, my students are using all sorts of other software and hardware, and they need that to communicate with the machine learning components. So we need to talk about ways to do that efficiently. Once I had articulated these learning objectives, it was fairly straightforward to think about student activities that aligned with each of them. And this eventually turned into the course curriculum for my classes. So for instance, here you see some of the week-by-week curriculum for my Cadenze MOOC. Each lecture and activity here is aligned with very explicitly with a number of these learning objectives. All right, let's move on. Another activity I've spent a lot of time on is developing scaffolding tools for experiential learning. So if we go back to Biggs's constructive alignment, for instance, we're reminded that students learn from what they do, not what we tell them in lecture, not what they read, but what they do. Scaffolding tools can make it easier for learners to engage in meaningful tasks. And here, they can engage in meaningful tasks with machine learning even as beginners, even if they're not professional programmers, even if they lack other skills that machine learning researchers or professionals may have. One of the technologies I use a lot in my teaching is Wekinator. This is a software program that I first developed in 2008 to support professional creators in music and art. It's been downloaded over 25,000 times in the last few years. It's used in professional practice and teaching, especially creative computing teaching around the world. So it's gone beyond my initial design at this point. But Wekinator is a domain agnostic GUI-based tool for real-time supervised learning. It just receives data from some kind of real-time feature extractor, which could be from sensors or audio or video or something else. And then it takes the outputs from the trained models and sends them to other software. Again, could be animation, sound, game engine, kind of whatever you want. Inside, Wekinator does the machine learning stuff. It provides an interface for users to create training examples, including from real-time demonstrations of gestures or sounds, for instance. It allows you to build classification, regression, and temporal models. It allows you to run these trained models on real-time data, and then to manage all of the machine learning stuff, the basic things like changing the algorithm, the feature selection, computing, model accuracy, and so on. So you could think of Wekinator itself as a type of scaffolding tool. It makes it very easy for anyone to start experimenting with supervised learning without knowing much about how machine learning algorithms work and without needing to program. But on its own, it's not sufficient, right? You need to send it data from somewhere, and you ideally want it to control something interesting rather than just showing you numbers on the screen as the models compute new values. So to support my teaching, I've developed a number of accompanying scaffolding tools that allow beginning students to make completely functional interactive projects without any code. So I've built over 25 example feature extractors that can send data to Wekinator from audio, from video, from Arduinos, game controllers, lots of examples in a lot of different languages like open frameworks, Python, processing, languages that my students, if they are programmers, are often already using. Likewise, I've built a number of example programs that respond to Wekinator data from trained models. These might make audio or music, animations, they might connect to physical computing systems or games, and again, using a lot of programming environments that my students are already likely to be familiar with. You can mix and match these components. So students might grab a video face tracker built in Open Frameworks and use it to control a music synthesizer built in processing. Or they could take a Leap Motion and build a hand gesture controlled particle system animation, or they could do any number of other things. So usually in my teaching, this is the first hands-on activity that students do. So right away in the first lab, they're creating a new machine learning system that actually works, that analyzes and responds to their actions in some way. All right. I've built another set of scaffolding tools which plug into Wekinator called the Classification Explorer and Regression Explorer. These tools don't help you build a real system, but rather they enable students to explore the impact that different algorithms and different properties of training sets have on trained models. So here's a quick video of the Classification Explorer. The idea here is you can just generate some training examples by clicking in this 2D feature space. You can train a learning algorithm on this data set and then see what it does, visualize the decision boundary that it comes up with. Critically, that you can then experiment, right? You can change the training data. Here I'm adding some new examples. I'll use the same algorithm, but build a new model from this new training set and see what happens. And here I've got a one nearest neighbor classifier, and so it's very obvious how this classifier responds to this new, perhaps, noise in the data. We could change parameters of the algorithm, here changing the number of neighbors and seeing how the algorithm differs now in this new parameterization. And of course, you're not limited to reasonable choices of parameters. Students can try to break this in different ways and see what happens and test their assumptions about how algorithms work against what they observe. You can, of course, choose different learning algorithms and see how they might respond, building different decision boundaries on the same training set, and so on. So there's a lot you can do with this, both in very unstructured exploration, like you were seeing in the video, and in more structured assignments, where I might ask students to try to recreate certain decision boundaries, or to explore and see how few examples they might need, or how many examples they might need in order to build a particular type of model. All right, so a few reflections that I want to share about these tools before moving on in my talk. So again, these example inputs and outputs that connect to Wekinator, these have been really, really helpful in labs. Not just in the introductory lab where it's fun to get students building something that's relevant to them right off the bat, but also in later labs as we focus on, maybe the details of aspects of machine learning that might seem very far removed from everyday life, right? They can still plug in a feature extractor, a synthesis or animation or game into their machine learning system and be observing how the things that we're learning about have a real world impact in those tasks. And of course, they don't have to spend lots of time programming to do that. That's just kind of there for free. But also these scaffolding tools often become part of students' final projects. It was really useful, I think, to provide students with tools in a wide variety of programming languages, because my students have, they all have their sort of favorite environment, and that differs a lot from one student to the next. But giving them this sort of boilerplate code in these example programs meant that they could start tweaking the code, making something that maybe reflected their own creative ideas a little bit better as the term went on, but they didn't have to necessarily deal with all of the uninteresting operations of getting data in and out, for instance. The Explorer programs became a pretty core part of how I introduce different algorithms and how I get students to explore not just what algorithm is best on a given data set, but how do all these different factors interact when you might have different amounts of noise or greater or fewer examples or maybe unbalanced classes and so on, and really trying to get a feel for how these affect what a model is going to be able to learn. There are some caveats, though, and I think I wrote about these a bit in the paper. For instance, lots of real-world machine learning problems have many more than 2 features, and generally we have more examples than you can create easily by clicking on the screen. And so one of the really unexpected outcomes of this was that students found it really hard when sometimes they had algorithms like SVM or neural networks that really did better when they had over 30 examples to train. And they said, well, these algorithms might be hard to train. And the fact is, of course, you're almost always going to have many more examples than that in a real world context, and you're not going to have to click by hand in order to add them. So that's not necessarily part of something that should factor into your reasoning when choosing a new algorithm. All right, so next I want to share some examples of a couple formative assessments that I've developed for my students to briefly describe how I've used these in reflective teaching practice and in research about teaching. That is, I'm interested in how these assessments can help me learn about my students and to learn about how my students are learning. So briefly, the first example I'll discuss is a beginning of class brainstorming activity. This activity happens just after the first lecture in which I introduce the basic, supervised learning structure or pipeline. I describe how supervised learning algorithms are a tool for making model functions that compute outputs from inputs, and how learning algorithms build these models from training examples. And I show some examples, some demonstrations using Wekinator to build some simple audio and visual models as well. Students' first activity is to train and run Wekinator with some of the examples, as I mentioned. But then after this, I get them to brainstorm a list of scenarios in which supervised learning could be used in things that they care about. In their case, this is how could supervised learning be used to make a piece of interactive art or music. And as I've mentioned, of course, every activity we do is aligned to one or more of our learning objectives. This one targets these first two. I want students to understand the structure of supervised learning problems, the capability of supervised learning algorithms, and identify feasible uses of ML in new projects. In order to learn from this activity myself, as an educator and a researcher, of course, I had to do more than just mark the assignments and give students feedback, right? I actually had to approach this as a data set that I might want to analyze and derive some knowledge from. So I started with some questions of interest to me. So I wanted to know, are the ideas that students come up with feasible, right? Am I giving them something useful at the beginning of this class that allows them to think usefully in this space? Do their ideas differ substantially from the examples I've described in class, or are they just parroting back the weird things that I've chosen as things that they might want to know about? And likewise, what might be the challenges in turning their ideas into real projects? What kinds of things might I not be anticipating as an educator, and the sorts of things that people might want to do, and what skills they're going to need in order to get there? So I used a really, really simple standard qualitative coding approach to this data, coding, for instance, every idea according to whether it was feasible, looking at the domains in which students were proposing projects and coding those using a sort of open coding scheme, saying same thing for trying to identify what types of challenges might arise, but also keeping an eye out for other emerging phenomena, things that I hadn't necessarily anticipated as an instructor, but clues that might help me learn more about my students, where they were coming into the class, where we might be heading, and what challenges might be in front of us. I want to make it really clear here that even though this was the lightest of lightweight qualitative data analysis tasks, this kind of thing can be really time consuming. So I just took 30 brainstorming examples and I threw everything else out, and that was more than enough to dig into and learn some interesting things from, and be quite tired at the end. So this was an important part of the work as well. So let's briefly talk about the outcomes here. So I was very happy to see that the ideas that students came up with were very diverse. They were very interesting, and 27 of the 30 that I looked at were in fact feasible. This was a great sign for me because this suggested that the activities we'd done so far in class were a good starting point for beginners to begin to connect machine learning to the kinds of real-world projects that they were interested in. And they were clearly interested in a lot of really different things. Beyond that, there were some interesting findings that did influence my teaching. So one thing that came up, which was notable, was that feature engineering was often a potential challenge for realizing a lot of the ideas that students came up with. So for 14 of the 27 feasible projects, I looked at them and realized, you know what, this would be really hard, if not impossible, for a student to build just using the raw data that they have coming from the sensors or from the audio or video, that really they would need to learn about features, feature learning or transfer learning, feature engineering practices in order to achieve projects such as these. And that was part of my teaching curriculum at that point. It's become an even stronger part of my curriculum over the past few years. Another very interesting finding was that most of the scenarios that students proposed didn't strictly require machine learning. I looked at them. I'm a expert programmer, and I said, well, I could program this. What's the point of machine learning? And initially, this was kind of upsetting because I thought, well, why am I wasting my time teaching them a whole semester worth of content if they don't actually need this stuff? But then, on further reflection, I'm glad that I saw that because it helped me understand more of where my students were coming from and how that was different to, where I wanted them to be, right? These were beginning students. They didn't yet have a good understanding of what machine learning was capable of. They didn't have a good understanding yet of when machine learning might be preferable to programming or vice versa. But another observation here is that many of these students were relatively beginner programmers. Many of them had tried to program interactive systems with media or with sensors, and they had found it unsurprisingly very difficult. And for them, they often looked at machine learning at this point and might have said, hey, you know what, this seems easier than the way I've been doing things before. Who cares if machine learning is required or not? But it might actually have, in fact, be easier for them to use machine learning rather than programming. And so that's something to keep in mind with these students. All right, the last example I'll give is this one. So this happens in roughly week 3 of my in-person course after students have been introduced to a variety of classification and regression algorithms. So we've learned about these algorithms in a little bit of detail. They've gained lots of hands-on practice with them, with Wekinator, with the classifier and regression explorer scaffolding tools. And now I'm really interested in how they can synthesize this information in order to make good decisions about structuring projects. So their assignment as a group is to draw a decision tree or a flowchart for choosing a supervised learning algorithm for a new creative application. This chart should show someone how to decide which algorithm to use. That is, the leaves at the bottom of the tree should correspond to one of the above algorithms, which I list, or possibly use something else if none of these algorithms are appropriate. Again, this is matched to one of our learning objectives, which is I want students to be able to reason about properties of algorithms, data, and the problem domain to make sensible choices about algorithms and features for a new project. I started out with some questions, right? Can students come up with a reasonable plan of action? Are they able to synthesize this messy knowledge that they've been grappling with over the last few weeks? And what else can I learn about student learning and misconceptions? Again, I used a very, very simple qualitative data analysis approach, coding each leaf level decision node for, is this a reasonable decision given, the properties that they're looking at and the algorithms they're telling me to choose based on what's in that node. And for every node in the tree, what kinds of criteria are they looking at to make this decision? Are they looking at just properties of the algorithms? Are they considering data? Are they considering processing power, other real world phenomena that are important? But also, what else can I learn from this that maybe I didn't know before about my students? So most of the trees looked, something kind of like this, not too complicated, but fairly complex. There's a mixture of some, I would say, reasonable questions like, can your input data contain unwanted noise? Do you have a large amount of training data and processing power? And then there's some sort of questionable decision nodes like, do you require a complex solution? It's like, well, I don't know. Do I require a complex solution? That's kind of hard to answer without knowing more about the problem. In fact, that's kind of hard to answer without running an experiment. So the outcomes here, just to summarize, on one hand, students could often identify relevant factors that you really do want to consider when thinking about what algorithm to choose, and they could match them with individual algorithms, right? They'd digested some of the learning about algorithm properties that we've been doing for the previous few weeks. However, a lot of the inner nodes in these decision trees were still not actionable, right? Not without empirical experimentation. So things like, should classes be chosen by probability? Or would you like your classifier to classify using drawing a decision boundary or finding a nearest data point, right? These are yes, they're properties of the algorithms, but they're not properties that are meaningful to us. And in fact, if we're faced with a question like that in practice, we want to probably empirically compare multiple algorithms. And notably, no student actually proposed that we run an experiment to make a decision. They all sort of had these trees that pretended that we could know exactly what algorithm to use in each circumstance. And so I realized following this that actually, as is, this activity could promote an inappropriate sense among students that knowledge and reasoning are sufficient to choose the right approach. And I use this to change my teaching, really emphasizing even more explicitly how much of an empirical activity, an experimental activity machine learning often is. That even people with PhDs in machine learning research often have to do experiments. We don't always know the right approach ourselves. And I found that this was often hard for students to believe, especially students who are taught that computer science is a domain in which there are right and wrong ways to do things, and that knowing something about an algorithm means that you know how to apply that algorithm. And they hadn't encountered this idea that, in fact, we don't know, and it's very contextually sensitive and requires experimentation. I also modified this assignment, enabling students to say, okay, I don't know what decision to make here, so my decision node is going to be run an experiment and then decide. Okay, so I'll wrap up here with some final thoughts on research for machine learning teaching. A few years ago, an HCI and education researcher named Amy Ko wrote a fantastic blog post about why we need to learn more about how to teach machine learning. She writes that knowledge of how to apply machine learning to products is on high demand, but low supply. Journalists write endlessly about it, employers want engineers who have it, college students want to learn it, and yet almost no one actually knows it. And knowledge of how to teach machine learning effectively is also scarce and has been for some time. She goes on to write about her experiences learning machine learning at Carnegie Mellon, and they sound very similar to mine and perhaps many of yours. A sort of strange imbalance of theory-focused people who just show you lots of proofs and practice-focused people who might show you lots of tools, but ultimately lots of questions among students about how to really apply it in practice that go unanswered. Co provides a really nice structure for thinking about what it is that we need to do as researchers in machine learning and machine learning education, or just educators teaching students about machine learning. What is it that we need to do as a community to start fixing this problem and bootstrapping ourselves up into something that's a little bit more well thought out. And she draws on something called pedagogical content knowledge, which is a concept from education research, just the knowledge about how you teach something effectively. And she says, look, we need PCK about machine learning. And this will include useful representations for concepts, effective analogies, examples, and explanations, knowledge of which concepts in machine learning are difficult and why, knowledge of conceptions that learners bring to machine learning, methods of informally assessing knowledge, and common mistakes that learners may make when applying machine learning. So many of you from your own teaching, you probably have intuition about many of these things. You might even be starting to have some data about, more concretely, what is going on for your learners when you teach in different ways. And that's where I was when I started doing my research on this work. And this was a really useful framework for me to think about what aspects of what I was doing might be useful contributions back to the field in order to start to establish this knowledge. So I definitely encourage you to read her blog post. The last thing I'll say about this is that as I was doing this work that I've been talking about in this talk, I've added a few things to Co's call for MLPCK. So I've drawn on two other groups of researchers to add some questions that I really think we need to consider. So two questions are from Grossman's work. Grossman says, look, we also need to ask ourselves and have a good answer for why we're teaching this subject and what should be taught in the first place. I think we often skip over these questions in machine learning because it's so popular and everybody sort of has an idea that we need to teach, whatever latest technology there is, and maybe now, oh, we should do something about ethics, but we haven't done, I think, enough reflection as a community about what the details for the answers to these questions really look like. And then there's work by Mishra and Kohler about how technology is used in teaching, which they call technological pedagogical content knowledge. And again, I think in machine learning teaching, often we use technology because it's stuff that students are going to use in the real world. And that's often really useful, but we can also use technology for scaffolding tools. We can also question, how students learn the technology and the learning paths, and how does the technology factor into the objectives for our students who are achieving them. And I think we can be more reflective about that as well. All right, so with that, thank you very much for listening. You can find me on Twitter or online. Wekator and the examples are also on that website. So thank you very much.
Thank you, Rebecca. So we have time for questions now. If anyone wants to ask questions, you can do this now. Yeah, just unmute or write it in the chat.
I would actually have a question, Rebecca. Yeah. So what do you do with the research that you do about teaching? So can you publish that in a specific teaching journal, or do you present that more to like machine learners?
Yeah, so I guess there's a few different things that I've done so far. So the main publication I have on this is in the ACM Transactions on Computing Education. I also worked with a computing education researcher to try to put together a special issue of this. The editorial board of that journal was really enthusiastic about it, and I think they would love to have more papers from people teaching machine learning. There's also, I found a very enthusiastic community at the ICER conference. That's a computing education conference. We ran a machine learning education workshop there a few years ago, and that's really where a lot of this started out. That's where Amy Coe's blog post sort of originated. So I know that within the computing education community, lots of people are interested in this, and they're receptive. And then of course I do a lot within my own teaching. I find that personally the biggest impact is in just what I learn from this, how it changes the teaching that I do, how it changes the tools that I create, and how it changes the tone in my department. And we have a very collaborative department where people are obviously not everybody's doing machine learning, but we're trying to help each other be more reflective in our teaching practice. And this is something that I think we're doing pretty well at the moment.
Really cool. Thank you. Could you, maybe later post the links to the journal and the conference?
Absolutely. Yeah, I can do that. I'll do that in the chat.
Thank you. There's a question in the chat, Oliver.
Okay.
Good question. Is your research on how to teach ML specific to academic students? If so, which level? Would it be different in industry? Yeah, that's a great question. I think most of what I've talked about today is specific to undergraduate and master's level students, again, from that sort of creative computing background who have some programming knowledge, but not necessarily much machine learning or fundamental, computer science theory knowledge. I also teach a very similar curriculum in my MOOCs, which are targeted more at people who might be creative practitioners in industry. Now that's very different from data scientists in industry or programmers in industry. I think they aren't super different from my students in a lot of ways, other than they probably have more well-developed creative practices and are more expert in the surrounding tool set. But yeah, I think there are huge differences for other people in industry and for computer science students for that matter. I've done a little bit of work with collaborators thinking about how we could use these same kind of interactive, real-time, and even creative approaches with media in teaching computer science students. And there's certainly aspects of fun and experimentation there that are worth exploring, I think. But I'm definitely not going to claim that is the way to teach machine learning to other populations. I see Peter.
Yeah. Yes, just a quick question, more from the practical side, because this is something I typically see a challenge in. In terms of your learners, if you are in class, how do you deal with heterogeneous learner backgrounds? Saying that when you talk about or explain an ML algorithm and then somebody asks you, okay, so this optimization that you're talking about, so how does it work?
Yeah. No, that is such a part of creative computing teaching because, my master's students, for instance, I've got people who have computer science undergrads, I have people who have undergrads in like painting, right? They're very, very different. What I generally try to do is, create a class environment where, everybody is doing some of the same experimentation with the beginning scaffolding tools. We're having initial conversations that are really about higher level concepts, because at the end of the day, especially in this field, it's about what you can do with machine learning. It's not necessarily about like, oh, I've got, incrementally better optimization on this thing. At the same time, I really, for students who have the background to understand that, I want them to be challenged. I want them to be engaged. I want them to be able to build on that knowledge further. So what I often do is I've got additional lecture material. I've been doing a flipped classroom approach, so I have additional optional videos for those students. We've got, extra, sort of bonus activities for students. And then really importantly, all the stuff that I do is very project-based. So everybody knows from day one that they're going to be doing an independent creative project, and they can use any sort of machine learning, they can use any sort of tool, they can, do a deep dive into sort of research stuff, or they can make something that's just, completely bizarre in design world. And all of that can be fine. And then I have a lot of structure around that activity to make sure that, I get, give a lot of individual feedback on project proposals, making, helping students one-on-one, make sure that their independent work is a good fit for what their interests and skills are, helping them identify other resources that we weren't able to talk about in class that are specific for them. And then of course, being very available for one-on-one consultations throughout the term. And, of course, that relies on classes that aren't too huge, but I find it really rewarding.
So, yeah, I have still one question. How do you find the balance between theoretical background and practical content of your courses? So often if you focus on one or the other, yeah, you might have no experience in doing things, or vice versa, you lack often the knowledge of applying certain techniques properly. So do you have like a tip for how to balance these?
Yeah, I mean, it certainly is challenging. I think my approach, it's not a perfect approach, and there are pitfalls to it, but my approach is almost always to focus on the practical stuff, to say, look, this is what I want you to be able to build. We're going to talk about what you need to know to build this. And some of the theoretical knowledge can be sort of, you can come up with a proxy for that by saying, okay, here's some practical considerations that you might think about with this algorithm. If this thing doesn't work, you might try these things instead. And students might not have the background knowledge to understand why I'm saying these things, but it at least gives them a practical path to start out in building something. And then we can talk about, why, the reasons behind that if they're interested. Certainly, I hope that people are interested and that become curious about it and do some digging in themselves as well. But, like I said, at the end of the day, you can have a PhD in computer science and machine learning, and you still need to do lots of experimentation. So a lot of the other answer is to try to teach my students how to experiment with alternatives, try to build tools that allow them to do that experimentation effectively and efficiently. There's some other stuff that I've built for experimenting with feature engineering, for instance, that I didn't talk about today, because that's a really big challenge. Having a bit of knowledge goes a long way, but having good tools goes a long way as well. And just getting students to think in that way, I think is even more important than saying, well, I need to know everything, and I need to know everything down to the deepest level, because that's only going to get you so far.